Hi, my name is Dave O'Connor, Managing Director of Swagelok, Indiana, Cincinnati. On behalf of the entire team at Swagelok, I'd like to welcome you to our continued series of technical talks. Today's will focus on advanced regulator selection and troubleshooting, and is a follow-up to a tech talk we held on regulator basics. We're very fortunate today to be joined by Wouter Pronk, Swagelok Senior Field Engineer with over 27 years of experience selecting and troubleshooting pressure regulator issues. As always, we see this as a great opportunity for us to learn together. So I encourage you to send any questions or feedback to sherry.ross@swagelok.com. Thank you again for your support of Swagelok, and at this point I will turn it over to Wouter. Thank you.
Welcome into today's session for pressure regulator next level. If you were in the previous one where I did talk about how to select your perfect regulator, you might see some repeats, but my vision is always like the more you repeat and the more often you hear it, the better it arrives with you. So microphones and cameras from your side, please turn them off. And if you have questions, go through throughout the presentation. Do that by the Q&A button. A little bit about myself. I was introduced, and I think that was correct. So my name is Wouter Pronk. I'm based in the Netherlands. We say the Netherlands. I'm a pressure regulator tech lead. So I focus on training on pressure regulators like I do today, and training and mentoring a global team of pressure regulator specialists. So we have in 3 regions, one in Asia Pacific, in Europe, and in the US. We have 3 teams of field engineers, which are working at the distributorship, and basically they are trained up to the highest level. And if there are questions, we can also, they work together with me to get things solved. So it's correct. 28 years of pressure regulator experience, 17 years I've worked as a sales manager and salesperson at RHPS. That's the manufacturing of pressure regulators, which was acquired in 2010 by Swagelok. So since 2010 I did adopt also the K series, so the smaller regulators, the instrumentation regulators. And I'm the tech lead on these 2 series, so to promote them, to train people on it. So today we will talk about, again, how to select correct regulators with things we have to be aware of. Is there a difference between liquid and a gas? That of course we know what liquid is. If I drink my tea, that's a liquid. Regulator preventive maintenance, that's important to know. We talk a bit about tank blanketing, and I will show a little bit about RHPS series versus K series. I'm not going to do like a sales talk. That's a job which is done by your sales and service center, but I just want to put some of our regulators in the spotlight so that you can remember it. So if you select a regulator, what is your selection criteria? So it's very important that if you select a regulator that you do it based on correct information. And that sounds weird, but very often if I talking with a customer and talking about an application, then I very often hear the word "I think." And if we start selecting a regulator because we think we know what is correct, basically we should know the correct process information. So pressures, temperatures, flow, material compatibility, that's all very important. It's also important that we know what we want to control. Do we want to control the upstream or the downstream system? So is that regulator controlling and reducing high pressure to low pressure, or is it the other way around? And it's nice if you understand a bit about the natural behavior or performance of a regulator. We all wish that we had a regulator which was connected to a high pressure source, which is set at 5 bar and which gives a fluent 5 bar outlet pressure. Unfortunately, it is possible, but then we have to do a lot of extra things. If we talk about standard regulators, we will see lockup, Droop, supply pressure effect. And we will go through them. So before we start talking about regulators, I always try to explain how a regulator is working. And the principle behind it is basically balancing of forces. Inside a regulator, we see several forces. So the first force is the force we all know, and I do not have the correct regulator in front of me, but if we turn the set knob, we compress a spring. So that's the force everybody knows. That's the force everybody will recognize. And then we have the poppet spring force. Inside the regulator is a poppet, and that poppet should be against the seat. And it can be done by a spring, and in the way we do it, it can be done with a tight diaphragm. But in our regulators, there is a force which is created by the spring. So that's number F2. And then we have a very important force. That's the force which is basically the outlet pressure, the force we try to achieve, which is pushed against the diaphragm. So the diaphragm will see the outlet pressure. And then there is another really important force, that is the inlet pressure force. You can think about the situation where your high pressure inlet, which is 6,000 psi, is going to a regulator. The regulator will receive that 6,000 psi at the inlet, and it will push the poppet, a poppet like this, into a seat. So there will be pressure over here, and over the area of the seat, there will be created a pressure. That's what we can calculate by multiplying the area with the pressure, which creates a force. All these forces should be in balance. So F1 is equal to F2, F3, F4. If we change one of the forces inside the regulator, something will change. And I keep telling you, if you are on top of this equation, you can explain most of the performance issues within the regulator. The other thing which is very important to know about the regulator, how is the regulator performing, and how can we show the way he performs? And the way we do it is showing or creating a flow curve. So this is a flow curve, a typical example of a flow curve. This is the axis of which we see the outlet pressure, so that's your set pressure. So this one is by example set at 60 psi, and this is the flow. At this point there is no flow, and at this point there's a lot of flow. And very often we like to use the regulator in the flat area of the flow curve, maybe I have to say a relatively flat area, because there is an effect which is called droop, which makes the flow curve a little bit on the slope. So we start at the lock-up area, then we run into the droop area, and then we run into the choke flow area. That's really at the end of your capacity of a regulator. You don't want to be there. If you want to use a regulator at that point, it's better to buy an orifice. So if we start working on calculating and figuring out what regulator we need process information. So if I start talking with a customer and the customer wants me to make an 100% official quote, then we can use the product selection procedure which we created within Swagelok, and within that procedure we will give you a form like this, and we have to collect all the information. So we want to know what is the connection, what is the fluid which goes through it, what is the function of the thing. Is it the pressure reducing? Is it the back pressure regulator? The connection size, type, so this is a European one with British standard parallel. The material, what kind of seat material do you want? What springs are allowed? What's the fluid, in this case hydrogen? We'd like to know what's the maximum and the lowest inlet pressure. We'd like to know the temperatures. We'd like to know the flow rate. And so all this information brings us to the point where we can start selecting a pressure regulator. And believe it or not, if I ask in a conversation, so I ask what is your process data, and I write it down in my notebook and I start working on it, or I give you this form and I let you write down all the information we need. Before you write it down, you will check it. You didn't check it when I was asking it. So basically this to write down the information brings us to the point where you give me the information, you sign it off, and we can select the correct regulator. So what are we controlling? Are we controlling upstream or downstream pressure? So this is a very simple drawing. We have a supply source, cylinders, we have a pressure reducing regulator, we have a process, and we have a back pressure regulator. This pressure reducing regulator is controlling the pressure downstream. This back pressure regulator is controlling the pressure upstream. The supply comes from cylinders. Which kind of effects can we see inside this application? So first we can see lockup, and I will go through it. What is lockup? If somebody opens the valves over there, you will see the first effect we will see on a regulator, which is lockup. Then we see supply pressure effect. If the pressure inside these cylinders goes down, and you set your pressure at 15 psi, your outlet pressure will go up. So supply pressure down, outlet pressure goes up. It's against your feelings. It's different than you expect. Normal people, when I started in regulators, I did expect that if inlet pressure drops, outlet pressure will drop as well. But this is the other way around, and it's all to do with balancing of forces. We will see droop effect in the process. We will see Joule-Thomson effect downstream the regulator because of compression, decompression. So to start about lockup. So what is lockup and how can you recognize it? So to show on this panel, you see the regulator which is set at a certain pressure. In this case, it's approximately 15 psi. This valve is closed at the moment. If I open this valve, this gauge will show that the pressure drops downstream. So downstream the regulator, there will be a sudden drop, and that's what we call droop. I hope it will work. So we open the valve, and this is a regulator which is a little bit prepared, so it shows a lot of droop. But this regulator is not broken. This is a normal performance effect which you can see inside the regulator. So we call it lockup. You can imagine that if you're using a regulator in the lockup area and there is a little bit of flow, because the lockup only shows up with a little bit of flow, that you might have a performance issue in your system. Where can we find lockup? If you go to the published flow curves, which you can find in our documentation, it's difficult to identify the lockup. If you go for a CTR, like we call it, so customer test report, to be sure that your regulator is doing exactly what you want, we can make this flow curve more precise. And on this one, you can see that lockup shows up and is over at something like 200 standard liters in a minute on this specific regulator. You can imagine that if you are working with regulators in an analyzer system and you've got a flow to the analyzer or from the analyzer, which is really low. And I found this example because we also do site evaluations, and I found this example where the flow from the analyzer or to the analyzer was 12 liters per hour, which is 0.2 liters per minute. So you can imagine if this is the only flow which is controlled and set by a pressure regulator, you will have an issue. The pressure jumps up and down, your analyzer gets all kinds of different pressures. So what is this customer doing? They created a bypass, or they created a little bit more flow. So it's always important to know if there is lockup and the flow is really steady, you will get a steady pressure. If you are fluctuating with your flow, then you also see fluctuation in your set pressure. So supply pressure effect, inlet dependency. I introduced it already. If the pressure in a cylinder drops, the outlet pressure goes up. Or if your inlet pressure goes up, your outlet pressure drops. So it's a balance. Inlet pressure down, outlet pressure up, and the other way around. Think about a situation where you are running a process. You've got a cylinder, you start with 200 bar inlet pressure. You want to have 5 bar outlet pressure. Sorry for the bars. I'm mixing PSIs and bars up, but that's a European habit. So if I have a set pressure 200 bar in, 5 bar out, and my inlet pressure drops over time, the outlet pressure will go up. And if your operator looks at the gauge and thinks, "Oh, I have to correct this," then he will turn the knob on the regulator a little bit backwards. So he corrects the pressure. But what if this cylinder is fully empty and he puts a full cylinder in place? What he does, he creates a high inlet pressure, and because a high inlet pressure will create a lower outlet pressure. So you already did decrease the setting of that regulator, so your regulator will not give any flow. So customers on the phone, like, "Sorry, Swagelok, your regulator is not working well." If we start talking about supply pressure effect and we explain that what you did, you understand it. So again, it is all to do with the forces inside the regulator. So the F1, F2, F3, and F4 force. So there's something changing inside your regulator. So if one of the forces, and in this case the inlet pressure force, which is basically the F4. That's the force against the poppet. If that's changing because your inlet pressure drops. So basically the inlet pressure force, that's number 4, is changing, is going down. I'm not touching the spring, the set spring. So there's only one thing which can change. That's the F3, the outlet pressure force. If this one force goes down, this one should go up, otherwise the balance is gone. So that's a quick explanation of supply pressure effect. I've got a video which shows this. This is a pressure regulator which has an inlet pressure which declines from 34 bar to 6 bar. Outlet pressure increases from 1.6 to 2 bar. So if you look to the pressures, so we are decreasing the pressure from approximately 450 psi. That's the inlet pressure, flows from left to right. And you can see that your outlet pressure goes up to a higher pressure. Supply pressure effect. How can we calculate it? If you go into the documentation, you can find this, by example, a KPR, a Swagelok regulator, small 1/4 inch inlet and 1/4 inch outlet, has a supply pressure effect of approximately 1%. So if my inlet pressure is set at 3600 psi, my outlet pressure is set at 550 psi. If my inlet pressure drops 1000 psi, then my outlet pressure, so inlet pressure goes down, outlet pressure goes up. 1% of 1000 psi is 10 psi, so my outlet pressure goes up to 60. Simple calculation, but the effect is there. How can we get away from this? We can do this by putting 2 regulators in a series. So we've got an inlet pressure at 3600 psi. This outlet pressure was set at 500 psi, and my final pressure is set at 50 psi. So my total supply pressure effect will be 1% of 1%. If we look to the effect which we see in here, so inlet pressure drops, in this case 2000 psi, outlet pressure goes up with 20 psi, so it goes up to 520. Hey, that's funny. So the second stage will see pressure going up. So my last stage will see pressure going down. So with dual stage reducing, you can prevent a pressure rise due to supply pressure effect. So we have a solution which is the KCY, that's 2 regulators in the body. We have a first stage, and the first stage brings the pressure to the second stage, and the second stage reduces the pressure to the final outlet pressure. This is a very compact solution. To build this one on panels is not always convenient, and especially if you want to have a vent option, a self vent option on this spring. So in case diaphragm breaks, you want to vent off to a safe place. Same on this side. If you want to have an extra connection on this side, this regulator gets quite long and it's difficult to build on a panel. So we have a standard solution which we call the GDP program, gas delivery program. And so we can build this kind of panels in our CS department, custom solutions. So we have a fixed set pressure first regulator, and we have our second stage on the panel, and we have all kind of regulators around it. We have a safety valve on the panel. So this is another solution we can supply to you. Gas delivery program. I think you already had a presentation on this, so I will not dive too deep in there. Then the other effect, it's talking about springs. So regulator flow increase and droop. So if you look to this regulator and you look to the spring, and especially focus on this area, you see a spring which has a certain length because it's compressed by the set screw. If we increase the flow, if we increase the flow downstream, then the pressure will drop over here. This valve will go open. So the valve goes down, the diaphragm goes down, diaphragm support plate goes down, and the spring gets longer. What is happening with the spring? So my spring gets longer. What's happening with the spring which gets longer? This one will lose force. So if there's less force on top of my diaphragm, you will see that effect in the outlet pressure. So again, this is back to the equation. What is changing? The F1 is changing. The F1 goes down. So something at the other side will go down as well. And the only thing which can go down is F3. So The spring inside the regulator is a very important part of a regulator, so always select a regulator with the correct spring. We'll come back to that later. That's the next slide. So if you select a spring, always select a spring which belongs to the set pressure range you want to work with. If you think I'm going to standardize on one regulator, so I want to use one regulator for all your application on site. So you want to control like 15 psi, 20 psi, or even 40 psi with one regulator. You make a mistake because you get a spring which is too strong. So instead of getting the weakest spring, you get this strong monster. And this strong monster will give you more droop than you want to see. So my advice is always select a regulator which fits to your application. If you want to control 100 psi, select the F, which is 0 to 100 psi. You will not have an issue like with the gauge. In the gauge, you would like to see the needle up or 75% of the scale. Regulators, you can use them to the full set pressure range. These regulators are built with some extra capacity. So they are not set, the maximum set pressure of a regulator is not, in this case, is not 0 to 100 psi. In the static situation, it will be set with 10% extra. So you can always use this regulator in the full scale. So I was talking about the flow curve, and a lot of people say, hey, this is a flow curve of a regulator, it looks good. So what is the optimal flow curve for this regulator, and what's the optimal flow range? And a lot of people tend to say, in the area where it is flat, I can use this flow curve. Or I can use the regulator which is connected to this flow curve. Unfortunately, that's not always true. You can use the flow curve to select what's going through the regulator, or basically what's going through the seat. But think about the situation I made over here. If you look to this flow curve, that looks really nice because it's relatively flat. If you think about what is happening in this regulator, this is a regulator which is reducing methane gas from a high to a low pressure. Basically, the inlet pressure is 1000 psi, which is written over here. And the outlet pressure is like 350 psi. And what I did, I selected different velocities. So I can select in the calculation program, and this is a program which is available for you on swagelok.com, the flow curve generator for RHPS series. You can create this flow curve. And if you play with the velocities in the line, so a standard for methane gas and maximum in your lines is approximately 164 feet per second. And that's the first line. So the yellow line is the industrial standard. And the second line, still the pressure didn't drop too much, but it's at 300 feet per second. So if you use this regulator in a half-inch line and are try to run 663 standard cubic feet through this regulator, you have to realize that your velocity in the line is extremely high. Higher than the industrial standard. So where do you find it back? A lot of pressure loss, a lot of noise, vibration, and maybe a regulator which is failing earlier than you expected. So the pressure regulator with a half-inch downstream line, the fluid is methane, at 164 feet per second, and the other line is 300 feet per second. And basically you shouldn't use a regulator at that velocity in the downstream line. Joule-Thomson effect. Joule-Thomson effect is always there in regulators which are reducing pressure from high to low. There will be a little bit of temperature drop. The temperature drop will be based on the pressure drop, and the amount of freezing you will see depends on how high is the environmental temperature, how much energy is there in the lines, do we have a heater up front. But this is something you need to be need to take in consideration. We can try to calculate this. We have our field engineers, they have access to this tool, and with the tool we can really calculate what's going on. So you see on this one, we started with the pressure at this point, we reduce it to this point. So basically if you want fight the Joule-Thomson effect to get back to the same temperature, we know how much power you have to put in there. This was a regulator which was used also in methane, and this customer unfortunately had the heater frozen, so there was something wrong in the system. I very often do get questions about liquid or gas flow calculations. Is there a big difference? Yes, there is a lot of difference. Is there a big difference in how we do the approach on calculations? Basically, not too much. Basically, if we do a calculation, and this is an example of a regulator, it looks very much like this one. If we do a calculation on this one, we first calculate the size we need for the seat in here. And then, based on the industrial standard velocity downstream the line, we calculate the size of the downstream line. The calculation of the seat is done with industrial standards. Is done with pressure differential. And the downstream line in the gas system is done with the standard velocities in the downstream line. So if we take the two calculations side by side, then in a gas calculation, the flow at the seat is based on differential pressure. So if there is a big differential pressure, so from 200 bar to 5 bar, easy peasy job for the regulator. But if the flow comes really close to if the inlet pressure really comes close to the outlet pressure, then we can get in a situation where we are going from a critical flow to a subcritical flow. And a subcritical flow is a flow where the inlet pressure is really close to the outlet pressure, so with a small differential pressure. So that can mean that you can come into a situation where you have to correct a lot of things on your flow. Some people call it a choke flow or a non-choke flow. In our industry, we call it the critical flow or subcritical flow. Then there is a gas correction factor for the seat, because hydrogen runs 3 times faster through this regulator than nitrogen. So if this regulator is good for 100 normal cubic meters or 100 standard cubic feet per minute, then it can do 3.5 times, sometimes 3.8 times more. Calculations are always done on cubic feet, standard cubic feet. It's always standard cubic feet. We like to know how much the process needs in standard or normal cubic meters or standard cubic feet per minute. Because it's a gas, we have to go back to the environmental circumstances in which the gas will be. There will be a Joule-Thomson effect on gases. And that Joule-Thomson effect will be different from a gas to a gas. We have gases which cool down. We have also gases like hydrogen will heat up. And the gas is compressible. Downstream line velocities differ also from gas to gas. We take downstream velocities in hydrogen 75 meters per second. For oxygen, it's really low. And then we go to liquid calculations. So the flow at the seat is again based on differential pressure. There is a small correction based on density. Basically, fluid is a fluid. It's not too much different if the density is a bit different. It's plus minus 10%. That's it. Unless you work with very extreme fluids like peanut butter, but I've never seen a pressure regulator on peanut butter. But so if you're extreme stuff, then it could be different. Liquids are not compressible, so calculations are done based on liters per minute, not normal liters per minute, liters per minute. If we have a low boiling point in that liquid, it's possible that because we are reducing, that the liquid starts boiling, so we get a dual phase streams. That's not really nice for regulators. Regulators don't like dual phase streams. And also what we see in regulators in liquids, that there is cavitation. And cavitation is really bad for regulators. So you see over here, this is an example of a part inside the regulator which was eaten away due to cavitation in a few hours. And the other thing which we need to take in consideration if we talk about a regulator which is over here, and you look to the connection which is in the regulator, then this is a 3/4 inch connection. If we put a fitting in there, we are reducing the outlet pressure. So we are also reducing your downstream line. So the internal diameter of the downstream line is not really big. If we connect flanges to the same regulator when we have high capacities, then the internal bore of the line is bigger. So the capacity of this regulator in the downstream line is bigger than if we worked with the tubing. So this is a 3/4 of an inch regulator connected to piping, and this is a 3/4 of an inch regulator connected to 3/4 inch tubing. So there is a capacity difference. I always get questions about regulator maintenance, and I would like to talk a little bit about it. If people ask me questions about, Wouter, what can I do to, and what is the best frequency for maintenance on site? And do we need to have a plan to do maintenance on regulators? I've got customers who are using regulators, and regulators are in use for years, and the customers forgetting that they have this regulator and that the regulator is working well. Because it is in a nice application. It is a clean application. There is not too much Joule-Thomson effect. There is no abrasive fluid in the regulator. It's not a liquid. It's a gas. Especially on high purity systems, it's extremely clean. So if regulators are used in a simple application, they will last forever. If you want to do maintenance on a regulator, my advice is always, if you're not sure about how difficult it is, open the regulator after a half year. So start somewhere. Try to figure out how the regulator looks like. If he's still in a good shape, then you can continue for another. So you will find out your maintenance intervals yourself. My advice is always, if you want to do maintenance on a regulator, never ever open a regulator without having spare parts available. So you can order spare parts for K series and also for the RHPS series. There are good manuals with it, so it's not too complicated. And on the K series, there need to buy some extra tools, and with the extra tools, you can create the necessary torque on building it together again. So the tools can be ordered. And then in each regulator manual, we also have like troubleshooting. So if somebody is asking me like this is happening, then I ask questions, and basically this is a problem and the reason why and the solution. So if the regulator, we call it creep, is leakage, then it's very normal that we change the seat. So replace the part inside the regulator. And so in this way we can go step by step through a regulator to repair stuff. But maintenance is part of a regulator life. It is a mechanical instrument, and most of the returns, because it's possible to send in regulators which do not perform in the way you expected, but most of the returns I'm not sure, so I think, but I heard numbers of 95% of the product returns we've got are based on contamination. So systems are not always as clean as you expect. Installation people and integrators are not working as clean as you think. A small burr can create a damage on the seat, which creates a leak. So maintenance is part of the regulator life. How can we prevent it? Use the tools, the correct tools. Put filters inside your inlet. Work with filters inside your lines. And another thing which I keep telling you, a regulator is a control instrument. A regulator is not a shut-off valve. So if you expect 100% shut-off from your pressure regulator, it might do it if it is brand new. But if it is used for a while and it has seen some abrasive stuff, the regulator is not 100% bubble tight anymore. So if you keep a system overnight without any flow, my advice is always close your upstream valves. And then another thing which is it's very actual at the moment, and we did talk in an earlier training about our GDP program. Swagelok will run into a lot of questions where customers are asking us, like, hey, what do we need at the supply point? Do we need a bottle rack, or do we work with a single regulator? What kind of manifolds do we need? Where do I reduce my pressure? Do I reduce my pressure at the bottle rack? Do I reduce my pressure at the point of use? Do I need an auto changeover panel at the bottle rack? So, and to figure out what you need, these are the things which I always take in consideration. So first of all, and that's the most important part, system safety. System safety to protect your people. And I think that's really important, to protect your people, that everybody has a safe working place. And it's also good that the system is protected, so that if there's some leakage inside the regulator, that is always protected with safety valve. The safe routing of lines. So always keep gases together. So, and never, if you have, like, very often you see in corridors, in labs, you see, like, in the corridor where you walk to your labs, and you look at the ceiling and you see all the lines coming there. It's not very safe to have, like, explosive gases and oxygen all in that area. So try to keep the lines which are kind of dangerous in a good position, in a good routing. So keep your gases separated, and also the lines separated by the type. Ventilation capacity of the building. Always take care that if something is wrong, so if somebody is working with regulators, and even with gases which are not poisonous, but which can push away oxygen, then be aware that there is enough ventilation to get away of nitrogen. Space management. How much room do we have? Can we work with small panels, or is there more room for design? Capacity calculations for now and in the future. Don't make the mistake to think this will be the lab I need and there will not be any future expansion. If it is at the lab table, it's fine. You can build an extra lab table. The line which goes from your pressure source into the lab, if that's not designed in a way that you can put an extra table in here, then not a very clever decision. Material compatibility. What kind of materials are going through it? In research labs, can be NACE, can be all kind of poisonous gases. Is it a single stage supply? Is it a dual stage supply? Is it diversity of pressure at the hookup? So do we need the first stage reducing over here and the second stage reducing over there? Or is every table equipped with the same pressure? So we have a dual stage reduction in here. Is it a constant delivery? So do we need to have a changeover valve? If a process is 24 hours per day, 7 days in a week, it's very important that the gas supply is guaranteed. So if you have got 2 sets of gas bottles which are connected to one auto changeover system, you have a constant gas supply. And then redundancy. If one of the systems is really important to you, and there is, it's important that there is a 24 hours, 7 days a week gas supply, it might be worth having a redundant system. So a parallel system which can be switched on if the other one is in maintenance. These are the questions I get a lot, which have to be taken in consideration. Then there is a question I get a lot about, hey, how do I control my regulator? So this type of regulator is very often in use. So to set the spring with a knob. The other option is to work with a dome loader. And a dome loaded regulator is basically the same body you see here, same body over here, but then there is a dome on top. So if you want to work remote, you can bring in gas in here, and the pressure which you put in here, like 5 bar, will be approximately the outlet pressure. And dome loading gives a few advantages. How does it look like? This is a dome loader, and I was asked to present a little bit about the RHPS series. So this is a typical dome loader. You see a nice 1.5 inch stainless steel dome loaded regulator with a pilot. So the pilot takes the inlet pressure, goes into the pilot, goes into the dome, and we create a dynamic leak to the outlet to have a constant outlet pressure. So we have a nice big diaphragm controlling the pressure. And if you want to control precise and accurate systems, and you want to do it as good as possible, my advice is always try to find the diaphragm which is as big as possible, and try to find the seat which is as small as possible. So the combination of a small seat, big diaphragm will give you the best performance. So if it's possible to select the correct regulator, do so. And if you are used to work with spring-loaded regulators, you know that you start with a small diaphragm, and if the outlet pressure is high, you start working with pistons. So the diaphragm or the sensing area gets smaller and smaller and smaller. So how accurate is a piston regulator? Not really accurate anymore. So that's why we designed dome-loaded regulators. You work with a full set pressure range with a nice big diaphragm. So the ratio between diaphragm and seat is always big. And that gives you a low supply pressure effect, and there is no spring, so lower droop, and remote control is possible. So if you have a test lab and you have a remote test in a bunker, you can control the regulator remote. One of the subjects I like to talk about as well is tank blanketing. Tank blanketing is basically having a storage, and in the storage there is very often a liquid, and you want to have like an inert environment on top of that liquid. We see a lot of applications which look like this, and people call this blanketing as well. So there is the fluid which goes in, so this level goes up and down. There's a vapor on top, and there's a fluid which goes out. So this is to the process, and this is basically your supplier for the fluids. People connect nitrogen to this side of the tank, put a flow meter in between, and they have a constant flow over the gas, and the outlet goes to a flare or to a safe place. And they take care about a constant inert environment on top of the liquid. If I see this, and I've seen it a lot, people say, yeah, that's the way we do it. And then my question is always, who's the happy person in this application? I can tell you that's the gas supplier. The gas supplier will be really happy about this, because they keep supplying the nitrogen to this system. So how to get away from this? Is very often I talk with customers and ask them, how much nitrogen do you use? And they don't really know immediately, but they ask at the purchasing department, and they find out that they buy a lot of nitrogen. So very easy to suggest to build it in this way. So if you have a tank with a fluid, your fluid goes in, fluid goes out, level goes down and up. If it goes up, the nitrogen which is in here will be pushed away to the safe place. If the level goes down, the blanketing regulator will supply nitrogen on top of the fluid. In case the purchasing department, we can always blame them, if the purchasing department forgot to buy nitrogen, we have an issue. Think about a tank which is in here, and the tank is under a certain pressure, and the level goes down. You create a vacuum over here, and you don't want to have a vacuum in a storage like this. Storages like this are always very, very fragile. And why? Because storage liquid, they want to build it as cheap as possible and with a thin wall thickness. And the pressures which are normally used in this kind of storage are low. So 0.15 to 0.73 of a PSI. So the pressures are low, and the reducing regulator is set a little bit lower than the back pressure regulator. So this one is set at a lower pressure, and this one is set a little bit higher pressure. If the level goes up, this starts venting, and if the level goes down, this one starts supplying. And the regulator you see on top over here is the vacuum breaker, and the vacuum breaker takes care in case there is no nitrogen supply anymore and the level goes down. So we create a vacuum in this tank, and we don't want to see it because the tank can collapse. I have a picture later on. Then this valve will open and will put atmospheric pressure inside the tank. It's not okay, and there should be an alarm on that, but you save your tank. It's better saving your tank than having a tank which implodes. So why do we do blanketing? To prevent air from entering a storage of a vessel, to prevent that an explosive mixture develops in the vapor space. So if we want to have a fire or an explosion, we need fuel, we need oxygen, and we need ignition. If you take away one of the three, you create a safe environment. So very often, if you take the oxygen away, replace it with nitrogen, you create a very safe system. So air contains oxygen, moisture and other contaminants, which can lead to internal corrosion and also the degradation of the stored product. So think about a pharmaceutical plant where you have like a clean process and you want to keep that process as clean as possible. You can control the quality of your nitrogen, which is supplied by your gas supplier. So very often systems like this are vacuumized, filled with nitrogen, vacuumized, filled with nitrogen, vacuumized, filled with nitrogen, sometimes 5 times. So they're 100% sure that the environment is as clean as possible, so that they have 99.9999% of nitrogen on top. What's in such a pharmaceutical process is extremely expensive. So we want to treat it like gold. So we don't want to see any oxidation of the product which is in the tank. And this is what the picture I was referring to. You don't want to be the person who organized this, unless you are the person who pulls tanks like this down. But this is just a little bit of vacuum, and if you go on site online and you go for the YouTube, you can find a lot of nice pictures about tanks which imploded just by a little bit of vacuum. Another thing which we need to think of, if we have a tank which has a low pressure inside and it's nice and warm, and all of a sudden we get a thunderstorm and we get hail, we got a quick cooling effect, then that quick cooling effect will create a vacuum as well. So the calculation of the supply regulator should be correct. If the calculation is not done correct, you can have a risk of implosions as well. If you have a small supply flow into the tank, you will get a pressure which is too low and you can get this kind of situations. What is a typical tank top? On a typical tank top, you will see regulators installed like this. So this is a TBRS8, the 1-inch connections, and this is the TBVS8. So V stands for vent, and the R in this name stands for reducing. The regulators are installed with the diaphragms in a vertical position. So the diaphragms are in this position and not in this position, and you can see why. So they are set at really low pressures. And so sometimes the weight of a diaphragm can already influence your set pressure. So if it is installed like this, you have no influence from the weight of the diaphragm, and you also have a good drainability of your valves which are installed. So tank blanketing, pharmaceutical plants, small processes. So in this plant you see first the regulator was doing the purging, so purging of the vessel. This regulator takes care about the pressure in here. And what markets are we in with tank blanketing regulators? We are in the smaller market. There's a smaller batch processing. We are not on the big tank farms. We can't replace the big carbon tank blanketing systems which you find on the big storage tanks. We are in the smaller processes. So finally, I want to go a little bit over, give you a little bit overview about what's the difference between the two series we've got. So we have got K-series regulators. So these are the K-series regulators. They are used in instrumentation. So you see heated regulators, you see dual stage regulators, and we also have the process regulators, which are the RHPS series. So this is the regulator I showed you on the table. This is a nice big dome-loaded regulator. We've got back pressure regulators, tank blanketing regulators, back pressure dome loaders, and a pharmaceutical regulator. So this is the overview. Funny enough, if you look at this overview, a lot of people buy and they open the documentation and stop at page 6. And why do they stop at page 6? Because they think that this regulator can handle my inlet pressure and it can control my outlet pressure. So I select this regulator. But if they go one page further, you will find that the KCY, which is able to do a dual stage regulation, so which can give you a better supply pressure effect. If you want to control a very low pressure, it's better to work with a KLF. So my advice is we design different regulators because of different applications. Try to find the regulator which fits your application. It will be very beneficial to do it that way. So these are the pressure reducing regulators. These are the back pressure regulators. And these are the special ones So we have like the dual stage regulators, we have an auto switch over system, and we also have heated regulators, so the KV series. And for the RHPS series, so we have the downloaded regulators, we have the back pressure regulators. A lot of people ask me, why do we have red knobs and blue knobs? The red, that was my boss, he thought about, hey, reducing, that's red, the R from red, and the back pressure regulator, B from blue, so we put a blue set knob on this. So this is a downloaded pressure reducing regulator. This is a downloaded back pressure regulator. This is an air-loaded ratio regulator. This is a tank blanketing regulator. This is a sanitary pressure reducing regulator. And I will highlight two regulators which might be of your interest. So the RHPS has a differential pressure regulator, and the differential pressure regulator is a regulator which can be controlled by dome, so by a reference pressure which you put inside the dome in here, but you can also set a bias. So this regulator takes care about the set pressure, which is, by example, 7 psi higher than a pressure which comes from a system. So in this connection, we put a reference pressure, by example, the pressure from a seal or a mechanical seal, and we want to have a little bit higher pressure on the mechanical seal. So this is the pressure from the pump, and the outlet pressure goes to the mechanical seal. So this is the differential pressure regulator. And we have also the dome-loaded ratio regulator, which makes you able to control a high pressure with a low pressure. So this regulator has a ratio 1:15, 1:40, 1:70 in the way it is built. So the ratio is between this diaphragm and this piston. So if you put 1 bar in here, if you put 1 bar on the control diaphragm, and you use the ratio 1:15, your outlet pressure will be 15 bar. If you use the 1:70, the outlet pressure will be 70 bar. If you use the 1:40, your outlet pressure will be 40 bar, as long as you have sufficient inlet pressure. So if you put a very precise electronic pilot on top, and my advice is always to use an electronic pilot which is really precise, because if you make a small mistake, you will be punished 15 times, 40 times, or 70 times. So this is a regulator we sell very often in mechanical seal systems. In test laboratory. This one is sold very often in mechanical seal systems, especially on the gas dry panels. And this one is used in test panels for testing engines, testing electronic parts. And they're also used in our test benches on the Isle of Man, where the regulators are manufactured. So we have something like 10 test benches, and all the test benches are equipped with this regulator, doing a hell of a job. So this was the conversation for today and the training for today. And if there are any questions, I'm really curious to know, and I will try to answer them or right now or later on by email.